generated by respiration. So if you subtract off, because you don't think it's contributing to respiration, a higher number for non-mitochondrial respiration, you subtract off a lower carbon dioxide value from your total proton production. And that leaves you with a higher glycolytic rate and therefore a higher rate of glycolytic ATP production. But that's a really great observation because these two rates are linked relative to total ATP production. So it's not just that changing the respiration values changes only oxidative ATP production. You've seen clearly that it also changes glycolytic ATP production. So when we're talking about glycolytic and oxidative ATP production, it's important not to attribute the glycolytic ATP production to only a function of the acidification rate. Equally, it's important not to attribute oxidative ATP production to only a function of coupled respiration. That's why it's really important to keep the whole trace in mind when you're working through the calculation. And that's why it's important to collect the whole trace in order to make the calculation in the first place. Any other observations or things that you noticed that I missed or haven't talked about yet?
I think we didn't discuss how, theoretically glycolysis would compensate for decreasing OCR with oligomycin or rotenone mixothiazole, but also the idea that capacity of glycolysis is involved, and so that compensation might not be complete if we are reaching the limit of our glycolytic capacity.
You're absolutely right. So when we mess with these numbers, we are not maintaining homeostasis at all. The manipulations here are really just meant to demonstrate how these values affect the calculated rates, but we are not modeling a homeostatic cell. Is that the point you were making, Daniel?
I was just saying that as a portion of, glycolysis compensates for oxidative or for OCR when we're talking about JATP. And so if you shut off OCR and you still want to make the same ATP, then you're going to have to increase glycolysis. And absolutely, the ability of cells to increase glycolysis is probably going to reach a limit that we just didn't discuss. So we don't know if this cell would necessarily respond glycolytically by increasing its rate of glycolysis if we were to use any of these compounds like rotenone mixothiazole or oligomycin.
You're right. And if we were trying to model the network responses in a cell, all of that would absolutely apply. But to the extent that we're really just looking at how these numbers influence the calculations, we can dispense with all of that and then just focus on developing. So the whole goal here is to try to develop a slight intuitive sense of how each of these measurements is affecting your ATP production rates, and trying to develop a sense of whether these values make sense to you based on these values and how much each one of these measurements influences your final rate.
So I have a question about kind of going back and forth between the ATP rate calculation and also the, I guess, the mito stress test, the respiratory control ratio. Mm-hmm. So if we see, for example, there's a compound or pathway, it's increasing ATP synthesis rate for, let's say, through oxidative phosphorylation, then do we also necessarily see that in terms of reserve respiratory capacity increase? Like, how do you go back and forth between, like?
I'm not sure I fully understand your question.
Let's say if we see here, based on the oligomycin and rotenone response, we calculate ATP synthesis rate is increased. And then if we go back in reserve respiratory capacity, do we also expect to see that's representative in terms of like FCCP response?
So if you have a compound that, for example, increases ATP demand, and you therefore see increased respiration or a little bit of increased glycolysis or both, that wouldn't necessarily change maximal respiration. So if you're asking about where the trace would change based on your intervention, it depends on what part of the rate it's affecting. So if it's still ATP demand limited, you would only expect it to change the basal rate, for example. You wouldn't expect it to change the oligomycin rate, which is the proton leak rate, and you wouldn't expect it to change the maximal respiration rate, but you would expect it to change, similar to cyclohexamide, the basal respiration rate. So I think it can be confusing to look at the different parts of the traits and to realize that they're all the same cell operating under different conditions, but that you need those conditions to define the parts of the trace that we care about relative to the phosphorylating portions of respiration and acidification. So I would separate those two ideas. We're using the separate parts of this trace to calculate rates of ATP production under one time point of condition. So one thing that I guess I haven't made clear until now is that when we talk about the total respiration and the total acidification, we're really using that term total to refer to the raw rate at a particular time. So for example, this data set is letting us calculate the ATP production rate at let's say this is at T equals 5 minutes. So before we've added any of the drugs, we're just looking at, for example, basal rates of ATP production. So say this was the measurement of respiration at 5 minutes. This was the rate of acidification at 5 minutes. All of these rates happened after that time within the same well. But this output is what was going on in that first 5-minute period. Does that make sense?
Jonah, I think you're not sharing your screen anymore. So
am I not showing my screen anymore?
Come out to a breakout room, you have to reset screen share.
I have it shared.
I can see it.
Yeah.
Okay, it's just me then.
Do you see it, Martin?
No, but carry on.
Okay. Okay, so we've gotten to the point where we can successfully and confidently evaluate the bioenergetic behavior of a cell. We can talk about whether it's primarily oxidative or glycolytic, and we can even talk about how much. And we have some understanding of how much the different parts of the trace contribute to the final calculation. So let's take a second now to look through this worksheet and really kind of poke at it and see what's underneath it, if I can advance my slides. So let's look at this. Let's look at how coupling efficiency affects our calculation. So if we go into this cell here, the oligomycin rate, you've maybe done this on your own already, but let's go ahead and change this value from 21.5 to 4.3. So let's make it match the non-mitochondrial respiration, implying that these cells are 100% coupled. That all of the respiration is either phosphorylating or it's non-mitochondrial. And we see a change from this to this. And I think Carl already explained this really well, which is that obviously when you increase the amount of phosphorylating respiratory signal, that corresponds with an increased ATP production rate. So I hope that this change makes sense to everybody. Is that true?
Yes.
Okay. What if we then went ahead and made, actually I can't do it here, but if we made both of these 0, you should see additional increases in the rate of oxidative ATP production. So I would invite you then on your own time to just change these numbers around a lot and see what happens. Let's explore something different. Oh, so we did that already, and now we've increased it a little bit higher. I forgot that I'd programmed that in there. So we alluded earlier to the contribution of the buffering power of the medium to part of the signal that we use to calculate, in this case, glycolytic ATP production. So this will be a demonstration in how linearly those two things are related to one another. So let's go up into our constants and conditions section up here. We've set our buffering power at 1. So, or sorry, 0.1. So 0.1 here refers to per picomole of H plus added, you get a 0.1 millipH unit change in your medium. Let's go ahead and double that. Let's change it to 0.2. But before we do that, what is going to happen, do you think, to glycolytic ATP production? So if you have already done it, don't say anything. If you haven't done it, let's make a prediction. Will the blue bar get bigger or will it get smaller?
Smaller,
Why will it get smaller?
because the buffering capacity is bigger, so you're not gonna see as much pH change in the medium or in the cell.
So if you see less of a change for the same rate, would you expect your column to rise or shrink? Why don't we go ahead and make the change and see what happens? So if we change the 0.1 to 0.2, we see that we have approximately the rate of glycolytic ATP production. Why? What just happened there? Have we increased our buffering power or decreased our buffering power? In other words, do we see a greater deflection of pH per unit of proton added or a smaller one?
You see a smaller one.
Right.
Let's look at these units one more time. So this unit, this value refers to the pH change that occurs on addition of a picomole of proton. So if before we saw a 0.1 unit deflection, and now we see a 0.2 unit deflection, are we seeing a bigger change per unit picomoles added or a smaller change?
Smaller.
Bigger change.
We're seeing a bigger change.
Yeah.
We see a 0.2 unit change per picomoles instead of a 0.1 unit change. And that means that the buffering of our medium is weaker. It changes more with more proton added. And what that means is that your measured rate of glycolysis is actually slower, which explains why the rate goes down when you weaken the buffering power of the medium. But the other thing to note is how much it changes. When we have the buffering power, so when we double the change that you see, you have the rate of glycolysis and you have roughly the rate of glycolytic ATP production. So you can see what a profound effect your assay medium has on the acidification rate that you measure. So this is a crucially important measurement to get right. And we've actually struggled a fair amount, even though measuring pH is very straightforward, but the context of that measurement appears to matter a lot. And so even though we don't always do this, what we recommend to everybody else is that you should do an in-plate calibration by injecting known amounts of HCl at the end of an assay or in a separate assay to really understand the buffering power of the medium. And so for everyone who's using the standard XFDMEM, that buffering value is actually already programmed in, but it never hurts to confirm that it's correct, just as a means of understanding your experiment. And if you ever change the medium and use a different one, it's crucial to understand the buffering of that medium in order to make an assessment of the ATP calculation. Any other observations about buffering power and its influence on glycolytic ATP production?
I had a question. If you use a different buffer with a different buffering power, the ECAR value would change, right?
Absolutely.
So then we could still have the same ATP production from glycolysis calculated here.
Absolutely.
Okay. Yeah, I just wanted to confirm.
But it tells you then how sensitive the acidification rate is to the medium. And it reinforces the idea that we mentioned earlier, that it's really hard to compare respiration rate and acidification rate, since acidification rate is linearly related to the buffering of the medium.
I have a question.
Go ahead.
So the buffering power that you're mentioning, should be measured using the seahorse pH meter? I mean, pH sensor? Well,
We used to say no, that it was equally good and easier to actually measure it externally using an external pH meter. However, that works for some media and not others. And the volumetric corrections that are made by the software don't always appear to line up with our external measurements of pH when we calibrate it externally. And so it's probably safer to do an in-plate calibration using the same sensors that are measuring the acidification rate in your experiment. So it's a little bit of a pain to set up, but it probably gives you a better calibration because it's in the same conditions in the same instrument measured in the same way.
thank you.
I have a quick question.
Mm-hmm.
What are some situations in which you wouldn't choose to use the XFDM that's just like standard seahorse medium?
So we typically use a minimal salts medium, like a Krebs Ringard phosphate buffered medium, and that's to marry our seahorse experiments with external experiments like microscopy. So if you're trying to make parallel measurements across different platforms, that's a reason not to use XFDMEM if XFDMEM isn't compatible with your other experiments. Other reasons include things like better control over your conditions. So if you want to specify what type of medium you're using, and it's not XFDMEM, for example, maybe your cells don't behave well in XFDMEM, they behave better in an RPMI-based medium, you would use that instead.
I have a
So
question.
reasons of experimental control are why you would choose to use a non-default assay medium.
I don't know if this is the spot for this question, but as people are starting to do IPSCs in Seahorse, I don't know if you've ever tried getting the media makeup of IPSCs for differentiation medias and everything, but they're not going to give it to you because it's
proprietary.
Exactly. So what do you suggest to people who can't figure out their pH, their buffering power of their media? Or, I mean, they have to guess it. They have to take a shot and just try to set it, even though they don't know what it is in their culture media.
I mean, if you have access to the medium, you can absolutely measure the buffering power.
Okay.
So that would be my response, that get a sample and measure it.
Cool.
So Seahorse has the 24 well plate setup, right? Is
Yeah.
it possible to like have one well where you just have media and add like inject four different?
Absolutely. I would never
Yeah.
base a calibration off of just one well though.
Yeah, I'm just like, is it possible to like manipulate, do your experiments in the same plate and then have a
That's
few
what
different?
we do. But actually that
Okay.
reminds me of something I should also say, which is that this is volume dependent. So the same medium, and what we've hidden here actually is that this is millipH per picomole per volume tracked and measured. And so if you assay the same medium in a 96 well and a 24 well, you will and you should get different buffering powers because this is per tracked volume. But that's something we can discuss more offline. Okay, so we understand that buffering power is an important determinant of measuring the acidification rate and therefore measuring glycolytic ATP production. And we can make the manipulation in the other direction and we can see how it grows. Now let's look at these parts. So in the first tab, we just looked at the raw measurements of respiration or OCAR and acidification or ECAR. And then the second table is all of these hidden calculations that let us understand ATP production rate. Checking on my time. Let's look at these wells for a second. So if you click on, I think it's currently 017, or the well that defines glycolytic ATP production. Let's take a look at these coefficients. So I hope that you had a chance to skim over the 2017 JBC paper that was in the recommended reading. It's actually essential reading to understanding what these values mean. So if you didn't, I hope that you take the opportunity soon to do that. And so I'll talk about these things now. But let's talk about what these values are. So we've got the N17 term times a multiplier, and we have this J17 times another multiplier. So let's look at the N17 one first. So this is the glycolytic proton production rate. So this is the extracellular certification that we have converted from pH units to proton production rate. And we've subtracted off the proton production that we can attribute to carbon dioxide. So we've isolated a glycolytic rate. We're multiplying this by 1. If you remember, 1 is the gearing ratio between the number of ATP generated per lactate produced. And since every lactate produces a proton, this ratio reflects the ratio of ATP production per measured glycolytic rate. We good so far? Okay, and then similarly, we have this other term. If you remember what we discussed prior, that not only are we accounting for ATP production from glucose that runs to lactate, but we're also accounting for glucose that runs to pyruvate that's then later oxidized. That oxidation is represented in the mitochondrial respiration rate. And we can gear that to ATP production using this P to O ratio, or this portion of the total P to O ratio. So I'm not really going to get into explaining how we get to 0.167. That's in the JBC paper. I'm happy to discuss it offline. But bear with me so far when I say that this is the P to O ratio for that ATP production rate from glycolysis to pyruvate that's later oxidized. So what we're doing here is simply adding up the two parts of ATP production that occur in glycolysis. And together, those two sum to the total rate that's in this cell. So it's mathematically simple. Conceptually, there's a little bit more buried under here, but we tried to explain it as simply as we could in the paper, and I'm happy to try to do so again offline. But the take home here is that we have a sum of two parts that yield glycolytic ATP production rate. So we can try to take a look at how much each one of these things contributes by changing these numbers around a little bit. So what I'd like you to do is first let's change this 0.167 value to 0. So leave this one alone for now. And let's just take this one. And so go right into the formula cell and just delete 761 and then the dot. So you should go from something that looks like this. So we have a 1 here and a 0.167 here to something that looks like this, which is not very different. So you can see that this rate has gone from about 40 to very slightly less than 40. So what does this tell you about the glycolytic ATP production that is accounted for by glucose that runs to pyruvate that's then later oxidized?
It's not consequential.
It's a surprisingly small amount. It's non-zero, but it's not a lot. Go ahead and correct this value back to 0.167, and then go ahead and change this 1 to a 0. When you've done that successfully, you should see something like this. So really the inverse of what we saw before. If we have two parts summing to a whole, and we surgically remove those parts one by one, we portion them out. So again, we see that when we change the ATP accountable by glucose to lactate, we change that to 0 and take it away, that accounts for most of the glycolytic ATP production rate that we see. So the take home here is that, at least under these conditions, the vast majority of glycolytic ATP production is actually accounted for by lactate. There's a small portion that's accounted for by glucose that runs to pyruvate that's later oxidized. And so one of the surprising things that we came away from this with was that, remember that these cells are respiring almost exclusively on exogenous glucose. So within the assumptions that we've made, so we assume that they are exclusively using that glucose, and we assume that they're completely oxidizing it or running it to lactate, which we can measure. And so what this says is that it takes a surprisingly small rate of flux of pyruvate into the TCA cycle to fully support the respiration that results. And most of the glucose that gets dumped in gets pushed to lactate and then exported.
And maybe it's worth pointing out that that's cell type dependent. So in the
Absolutely.
beta cells, was that what you're going to say anyway? In the
Yes, but it's good that you said it.
Was talking about you can't do this lactate export, so then it changes. Sorry, I didn't mean to jump ahead.
Great. It helps preserve the informality.
So going back to the buffering power, the answer seems kind of obvious, but you can't really compare two pieces of data with different buffering powers, right? Even if
not unless you convert them to the same units. So you could go ahead and convert everything to ATP production rate, and then you could absolutely compare it. But you cannot compare two acidification rates without knowing that so if the buffer is the same and you can assume that the buffering power is therefore the same, you can compare the acidification rates relatively safely. But you couldn't compare across experiments where the media were different and you didn't know what their different buffering powers were. Okay, so I hope
I have a question.
Oh, go ahead.
I'm sorry. So this is assuming that we are adding only glucose as a substrate. If we change the substrate, the OCAR and ECAR values will change. But will any of the other Excel numbers, will that change? Will we need to recalculate?
So for different single substrates, we do use the appropriate P to O ratios that we assume based on complete oxidation and the stoichiometry of those substrates. It gets a little trickier when we start using mixed substrates, which is one of the reasons that we tend to avoid the default XFDMEM that's usually supplemented with glucose pyruvate and glutamine, which is not to say that we haven't tried to reach some conclusions about mixed substrates, but what we usually do is assume that they're utilized equally, which we know probably isn't true, but errors in that assumption don't actually change the P to O values that much. So right now we're relying on the error of the measurement being larger than the errors that we make by assuming slightly wrong P to O values. But for single substrates, yes, so we do change the ratios based on the stoichiometries of those, the oxidation of those single substrates.
Thank you.
Okay, I've got half an hour left. So let's go ahead and run the same scrutiny of exploration on the respiratory, the oxidative ATP production constituents. So please go ahead and highlight cell P17. Its formula should pop up in the window above. And we see a very similar structure here, right? So again, like we mentioned before, there are two constituent parts of oxidative ATP production. And those are the ATP production that occur at the ATP synthase, so the coupled respiration rate multiplied by the P to O ratio for the ATP synthase. And then again, we're also accounting for that small portion that's attributable to substrate level phosphorylation in the TCA cycle at succinyl-CoA synthetase. So we then need to take into account the entire respiratory signal whether it's so both the proton leak and the coupled rate, because those both contribute to TCA cycle flux. And we multiply that by the P to O ratio for that portion of total ATP production. So what we can do now is the same thing that we did before and see how much each one of these things really contributes to the signals that we've generated for these cells under these conditions. So let's go ahead and do this sequentially. So let's start with the 0.121. Delete this term and just replace it with a 0. So let's get rid of substrate level phosphorylation in the TCA cycle and see what happens. We're starting out with this. When we change this value to 0, you should end up with something like this. What's changed here?
Not much.
Not much. Something small, but what is that small thing that's changed? What do we see drop? What would you expect it to see drop?
The glycolysis ATP.
Are we looking at glycolytic ATP right now?
Oh no, sorry. Yeah, you're right.
What do we got, Nastia? So are we looking at the blue column or the red column?
The red one, but I don't really see much change. Maybe it dropped a tiny bit.
It's a small drop. But yeah, you're right. So we've gone from just above 10 to just about 10. So again, this tells you about the relative contribution of substrate level phosphorylation in the TCA cycle to the overall oxidative ATP production, that when you remove it, you remove very little of that total rate. Let's do the opposite. Let's replace this with 0.121. So let me go back a second. And then go ahead and eliminate 2.486. Go ahead and make that 0. So when you do that successfully, you should see something like this. So what do we conclude from this analysis or this manipulation?
Substrate level phosphorylation has a very low control relative to every other component, relative to mitochondrial ATP production not related to that, or I guess electron transport chain activity.
So we're not really looking at either control or electron transport chain activity per se. We're just making mathematical manipulations to artificially take out different bits of the signal to understand the constituents.
But those constants that you have there should correspond to something that relates to control, right?
Now, these are just the P to O ratios. So these are just the gearing ratios that tell you what the relationship is between the rates that we're measuring. So the coupled respiration rate and the mitochondrial respiration rate, and what proportion of ATP they're generating. So what we're really understanding from this is that of all of the oxidative ATP production that is measured from these rates, most of it is chemiosmotic. Most of it occurs at the ATP synthase. A small portion of it occurs in the TCA cycle at succinyl-CoA synthetase. That's really all we're concluding from this. So we're not saying anything about control over flux. We're not manipulating those rates per se. We're just getting rid of different terms to see what's left, and therefore to see how proportionally these different terms contribute. Does that make sense? This is not a biological manipulation, so we're not trying to replicate anything experimental. We're just playing with the spreadsheet to look at the constituent parts of each of these rates. So if you're trying to consider the question, like how much of my ATP production overall comes from succinyl-CoA synthetase, it's that much, given the measurements that we've made up here. If you want to ask the question, how much of my ATP production comes from glycolysis to pyruvate that's then oxidized, it's the small portion that was left over on our prior analysis of the glycolytic ATP production. So I hope this leaves you with an understanding of how proportionally important each one of the phosphorylating reactions is as a proportion of the whole.
I have a question,
Mm-hmm.
vague, general one. Like, so in cells where you see more of the glycolysis pyruvate going into the TCA cycle and feeding the OXPHOS, would you see the same change here with the succinyl-CoA contribution to ATP production? Would there be an increase?
So you might, if you had more flux to the TCA cycle, you would probably have faster rates if everything balanced out. But interestingly, you would always have the same proportionality. Actually, never mind. I'm going to take back what I was just going to say. Yeah, so you will always have, if you have TCA cycle flux and if you have electron transport, you will always have ATP production of the ATP synthase, and you'll always have ATP production of the succinyl-CoA synthetase. And those rates will change depending on the fluxes through those systems.
What controls the TCA cycle flux? Sorry.
What controls TCA cycle flux? I mean, everything that we've been talking about over the last day and a half. So if we're talking about it relative to ATP demand, it's that increased ATP demand that's not met by glycolysis puts demand on the TCA cycle to provide electrons to the electron transport chain. So demand on respiration and glycolysis, the pull on respiration and glycolysis is set by ATP demand. And each of those two pathways then supplies or is a source of ATP production that meets that demand. And how those two are balanced depends on things like the substrate that you give it, the redox status of the NAD.
Thank you.
Okay. Okay, so I think for most of you, this is actually already deleted, but I wanted to make a few more points before we ended. So let's go ahead and look at our middle plot now. So when we looked at the summation plot in the OCARD, ECARD data, it was nonsensical. It was not a helpful thing to do. It was not a helpful operation. Is the same thing true here? Is this valuable? Is this a valuable thing to do?
Yes, it gives us an idea of how much total ATP is being produced by the cells.
Absolutely. It is one of the main advantages of being able to convert our two separate signals into the same units of ATP production. For the first time, we can sum these rates to understand total cellular ATP production. So this is an extremely valuable operation. It gives you information that you did not have before, even though we implicitly use it already when we were calculating percent glycolysis as a portion of the total. So this is extremely valuable information because using this, you can interpret changes that occur to either one of these pathways relative to the total rate of production. So for example, you can now distinguish, like let's say your glycolytic rate goes down, or sorry, glycolytic ATP production goes down, but respiratory ATP production goes up. And say that you've measured lactate efflux and you see that you have slower lactate efflux. You might conclude that there's something wrong with your cells. You might conclude that they are going into ATP crisis. But if you know that the total rate is the same, you might simply conclude that you've shifted ATP production from glycolysis to oxidation. So it's a crucial factor in allowing you to interpret a change that occurs in one of the rates if you've measured that rate. And that's really valuable and that's really important. So let's go ahead and take a look at this rightmost box, where we've done a similar operation as we looked at previously, where instead of summing these two plots in a column, we've plotted them into a dimensional space. And we've got glycolytic ATP production on the x-axis and oxidative ATP production on the y-axis. What can we say about this now? What does this tell us?
Isn't it the quiescent quadrant, like you explained before?
Yes, except that I hoped I made the point that those quadrant labels are meaningless.
It gives us sort of an operating line.
Yeah, so so these are, yeah, like, let's ignore the quadrants for a second. They're just marking these measurements. This allows you, unit by unit, to understand what any change that would occur to this system with a manipulation actually means. So for example, like we discussed before, if you made a manipulation that shifted your dot from this point to this point, so we go from this rate of respiration to this one, and we go from this rate of glycolytic ATP production to this one. Sorry, I should have said rate of oxidative ATP production. What do we conclude about this shift? Is there greater or lesser ATP demand on this cell with this change?
It's
The same.
It's the same. But what has changed?
Where the ATP comes from.
Where the ATP is coming from. So which pathways are providing the ATP that are being met under this condition than under this condition?
So here it shifts more to the oxidative phosphorylation versus glycolysis.
Mm-hmm. So we could speculate about something that we know that might cause this change. What might cause a decrease in glycolytic ATP production with a corresponding increase in oxidative ATP production without changing total ATP production?
Which substrates are present?
It could be a change in substrate.
Your buffering system?
I don't think it could be explained by a change in the buffering system, because we've already accounted for the role that buffering would play when we calculated these rates. Remember, we're looking at ATP production. So what is something that might explain a decrease in glycolysis with a corresponding and equal increase in oxidative ATP production?
Inhibition of LDH, lactate.
Sure.
Right?
Yeah. This could be an LDH inhibitor. We're speculating, but it's a possible explanation for something like that could generate this change. If we saw something like a change to here, what would that tell us? And we can draw a line between the axis, this point, and this point. And I'll try to make a 45-degree line here.
The ATP demand increased.
Mm-hmm.
And most of it is from.
Go ahead.
It's from glycolysis is meeting the demand.
Mm-hmm. Has the proportion of glycolysis changed from here to here as a function of the total ATP production?
No.
No. Yeah, so you can extract a lot of valuable information from this type of analysis. You can, if you've made a change that changes your rates, you can distinguish between things that change or don't change total ATP production by looking at whether this line is the same or not. You can look at whether the proportionality of contribution from glycolytic or oxidative ATP production has changed by looking at the proportions from the before and the after. And And then if we apply this further, and let's say we can put, let's say this was our maximum respiration and this was our maximum glycolytic rate. This is our max oxidative and this is our max glycolytic. What can we say about a cell that's operating here? What happened if we increased ATP demand an additional 10%?
It will start using the mitochondrial.
Yeah, if it
Oxidative.
wants to meet that ATP demand, it has to increase the respiratory contribution to the total ATP production rate. It has no more room to increase glycolytic ATP production because it's already hit its capacity under these conditions. So this lets you both understand a lot about what cells are doing, but also predict a fair amount about what cells might do if you change the conditions further. Okay, so I'm gonna have you guys go away for the next 5 minutes or so and try to play with the numbers in this tab to try to match each of these conditions. So try to find, let's try, so right now what we can see is that the glycolytic index, or the proportion of glycolytic ATP production to oxidative, as we calculated before, is about 80%. So let's try to pretend that we have made an intervention or identified a cell where that glycolytic index is 50. And I'd like to do that under 3 conditions. One, where you haven't changed the initial total ATP production rate of 53 picomoles ATP minute per microgram protein. One, where you clamp your glycolytic ATP production at its original rate, and one where you clamp the oxidative ATP production at its original rate. Does that series of questions make sense to everybody? You are trying to get ATP production to be equal from each pathways given different constraints of these different rates. So I'll let you guys go away and play with those numbers for a while, and then we'll reconvene and discuss in our last few minutes. Take a screenshot. You'll need to carry this with you. Ricky, could you? So did we have any luck trying to meet these conditions? So in the first prompt, you're being asked to find something where you have a point that is representing equal contributions of glycolytic and oxidative ATP production at a total JATP of 53 or so. So did anyone find a collection of respiration and acidification values that meet those requirements?
Yeah, we changed the total OCR value to 67 and the ECAR value to about 29, and
Okay.
we're able to get about 53 total ATP from half of each pathway.
Okay. Sounds good. That sounds about what I ended up doing. I'm sure there was more than one way to get to this point. But yeah, so you had to greatly increase respiration. You had to you had to decrease acidification. And that got you there. Did anyone have numbers that were substantially different from those? Around 70 and around 30 for OCAR and ECAR respectively, given the same assumptions about coupling efficiency and non-mitochondrial respiration. Did anybody change either of those 2 parameters? Did anyone change the oligomycin insensitive rate and the rotenone and mixothiazole insensitive rate? Nope, everyone just went for the total rates. That's fair, sounds good. What about the second prompt of trying to clamp the glycolytic ATP production, yet have a matching contribution from both pathways to the total? So that would look like this, where you had a glycolytic ATP production rate of 40.6. I'm not going to write out the 0.6. What did you have to do to get that change? What respiration rate yields an oxidative ATP production rate of 40.6, and then what total resulted from that? So this is the real question mark. Did anyone get that? Or an answer?
We raised the OCR value to about 88, which gave us a total JATP of 75. Oh, oops.
Anyone get something substantially different?
Didn't the 88 change the amount of JATP glycolysis?
Yeah, I realized, I think we started with a slightly different value when we were plugging things in on this one.
Okay. One of the things that I was hoping you would notice was when you made changes to the respiratory signal, how both the ATP production rates changed. And similarly, when you made changes to the acidification signal, how both ATP production rates changed. So this was a puzzle, not only in trying to keep your numbers clamped where I asked you to, but also to understand how each of the rates was changing, each of the ATP production rates was changing in response to the change to one or other of your raw measurements of respiration or acidification. How about this last prompt? I'll put this one here, of having an oxidative ATP production rate at 12.4, and then what glycolytic ATP or what acidification rate did you need under the conditions to match that? And then what do your total respiratory and acidification numbers look like to meet these last conditions? Any solutions?
This decreasing glycolysis by a lot.
You mean decreasing extracellular?
ECAR.
Yeah, how much? A lot-ish?
I have gone to like around 15 from 43.
Yeah.
But this is simpler than the middle one. The middle, I have not yet got to work.
Yeah, so if you haven't gotten these and you want to take some extra time to do so, I would go ahead and play with these. I think it's really interesting. It really helped me when I was putting it together, kind of develop a more intuitive sense of how these things were related to one another, at least under the conditions that these data were generated under. So again, the goal of this exercise was not to manipulate real experimental conditions. These things might or might not be experimentally achievable, but this is really a way that I think is helpful to understanding how the spreadsheet works and how changes in different values to the different elements of the spreadsheet will change your calculated ATP production rates. So I hope you've taken that away from this exercise. So I have a couple take-home points I want to make. Obviously, the spreadsheet has more tabs than this, so there's a second sample set that I highly recommend playing around with. In addition, what I can do is go ahead and share the Excel sheet itself with a couple of points, since I do have a little bit of extra time. But before I get there, let's summarize. So for total cellular ATP production, for a cell that's running both pathways, knowing only one of those pathways, or knowing the rates of only one of these pathways, is somewhat helpful, but not that helpful. Similar to knowing a latitude, but not a longitude. understanding ATP production rates from both of those pathways solves that problem and allows you to interpret a change in either of those rates with respect to and interpret it in the context of total cellular ATP production. And then further, we can dissect that on a little bit finer resolved level and understand the constituent phosphorylating reactions and their proportional contributions to total cellular ATP production as a function of their gearing ratios of the portions of those measurements to the ATP that's generated. Are there any questions about the spreadsheet, how it works, any generalities that I can answer? Let me go ahead.
It's probably cell type specific, but is there a good way to reference sort of these gearing ratios for different substrates and possibly different cell types?
Yeah, so we published the gearing ratios in the JBC paper. They're in table 1. So I can also go ahead and pull up that in our remaining time. But before I get there, let me go ahead and share the spreadsheet.
Maybe while you're doing that, I would just make a generalization from what you're saying, and that is that when most people use the seahorse with cells, they look at OCAR, and then occasionally they might glance at ECAR, and it's sort of going up and down. Maybe what you can take from this is that you should do more than just glance at ECAR and go, it's going up and down, but realize that it's a very valuable tool to understand the mechanism of whatever changes you see with your manipulation. Because as Shona said, it's a very different world you live in if the total ATP consumption has changed or whether it's switched between glycolysis and oxphos. And knowing which of those worlds you're living in makes your life a lot easier in terms of understanding what it is that your manipulation is doing mechanistically, and therefore how you should think about it or how you should fix it if it's a pathology that you're trying to fix.
Absolutely.
I'm curious if you've done this experiment where you infuse greater and greater amounts of anaplerotic substrates like glutamine or alanine and seen how that affects the trace in terms of oxygen consumption when there's already a normal level of glucose. Because you're doing this with only one fuel source, correct?
That's right. So we have actually run similar experiments where we've combined different substrates in pairs and in combinations. And so our confidence in the assumptions is weaker to the extent that our assumptions of the P to O values are slightly incorrect. But we have been able to understand a little bit about how different mixes of substrates contribute to different rates of respiration and glycolysis. So it should be obvious, but it was easy to demonstrate that, for example, if you give a cell glutamine and pyruvate, it doesn't run glycolysis, it can't. Whereas if you give a cell glutamine and pyruvate and glucose, it'll run glycolysis happily. And in fact, the total respiration rate tends to be a little bit higher, and it can support higher maximal respiration than a cell given a more limited set of substrates. And of course, that will also be cell type dependent. But we have explored a little bit of this space, even though our model gets a little more tenuous the further we go out from our validated assumptions. So
I was more asking, like, there are certain circumstances or stimuli that change whether or not those fuels are used as oxidative substrates or as biosynthetic substrates.
Yes.
And what I'm kind of curious about is I have a situation where I know that glutamine is used to create UDP-GLICNAC and not be oxidized under a certain stimulus. And if I basically use this trace to show that it's not actually going into the oxygen consumption pool as I add more glutamine, have you been able to demonstrate that basically oxidative substrates are either being used or not used on these tables depending on a particular state?
Right, so there is a lot of complexity underneath biology that we mostly ignore. And so one of the assumptions that feeds into what we assign as the P to O values is an assumption of complete oxidation of substrates. And so to the extent that that's not occurring, we ignore that change, partly because some of the back of the envelope calculations we've done to try to see what happens to the P to O ratios if cells are growing, and so they're partially oxidizing substrates. It doesn't change the P to O ratio enough that we would see it outside of the measurement error currently. But the inverse of that is that we couldn't use the seahorse to find those changes without either being able directly to measure the P to O and resolve the measurement accuracy to make sure we could distinguish changes that would occur with that change. So I guess the answer to your question is we ignore it and we can't see it. Okay, so in the spreadsheet, you'll see the tabs that we looked at earlier for sample 1. There's a second set of samples that carries a slightly different set of assumptions. This 5th tab here is a replica of the table that we published. And so what is currently input into this table are the data that are in that paper, or approximate data of that paper. One of the things that we get, or that I get asked about a lot in running the calculation sheet, is how all of these values are derived and where they come from. And I think it's really important to remember that these are qualitatively different types of values. And so for a given trace, so this is looking at 3 different parts of the same trace, or 3 different time sections of that trace. And so what is being shown here are the conditions under which we haven't given the cells any substrates yet. We have a respiration rate for that interval, and we have an acidification rate for that interval. And then further on in the trace, we input the oligomycin rate and the rotenone and mixithiazole rate. Within the same trace, we can calculate ATP production for the interval in which glucose is added. So these values will be different, but since it's the same trace, these values for oligomycin and rotenone are the same. And then similarly, we can go ahead and calculate ATP production in the presence of oligomycin. Again, these rates are different. You'll notice now that this time-matched rate is the same as the oligomycin rate, because this is the time interval in which oligomycin is present. And we're using the acidification rate from that same trace. So this is meant to emphasize how you use different parts of the same trace to calculate ATP production rates. And so this represents the data that I showed earlier, and I think it's in figure 3 of the JBC paper, when we looked at the 3 columns of total ATP production. This is that data set, and this is the calculation that underlies that figure. So this is the one that you can then expand with your own data set if you'd like. And then these last 2 tabs, which I almost never get to because we already run out of time, but I set these up because I think, again, this is a really helpful way to try to understand how manipulations change the output values. And so this is a toggle sheet where you can actually go and manipulate the gearing ratios to see what happens, for example, if you drop out ATP produced from glucose to lactate. So if I make a change from 1 to 0 by clicking on 0, the glycolytic rates fall away. And that tells you how much of that glycolytic rate is attributable to glycolysis to lactate. Similarly, if we're looking at the P to O of oxidative phosphorylation, for glucose, that portion of the P to O ratio is 2.486. If we're slightly wrong, if our assumptions are slightly off, our P to O ratios will change either lower or higher. And you can see where that changes the total ATP production rates. And of course, if we make that 0 artificially, we drop those rates out entirely. Again, similar to what we did earlier, if we drop out the ATP attributable to substrate level phosphorylation in the citric acid cycle, we again see relatively small changes. And then we can do the same thing through each of these. So this is, I think, hopefully a helpful way to understand, again, the proportional contributions of different ATP generating reactions to the total ATP production rate in a cell. And then lastly, I've set up the same toggle column instead of with column plots, instead with an XY plot. So now we can look at differences in the gearing ratios, but we can also look at things like if you run the experiment at the wrong pH. So say you run your experiment at pH 8 instead of pH 7.4. If we change this value here, we actually don't change very much. You'll see these values change a tiny bit, but unless you're looking at it, it's barely noticeable. So it tells you that while it's important to run it at the right pH, the wrong pH does not strongly affect your calculated results, even though it will obviously change the dissociation of carbon dioxide to bicarbonate and a proton. So that results in the changes that we're seeing here.
Just to clarify that, of course, the cells care about the pH.
Of course the cells care about the pH, yes.
Referring to here is the constants in the equations, and if you change the pH, what's the effect through that? The cells themselves would care a lot, so don't go running at pH.
Thank you, that's a helpful clarification. The other point that I was going to make also is that, yeah, as we mentioned before, the buffering power will profoundly change your calculated rates. So if that is wrong, you can see a much more noticeable shift in your glycolytic or your ATP production rates as a result. So we're shifting along the x-axis because we're changing the glycolytic ATP production rates that are calculated based on the buffering power of the medium.
And then the same comment on that, just picking up on what one of the participants said. Of course, you're not changing what the cells are doing.
Yes, absolutely.
So the cells are doing exactly the same thing. It's just that it comes out differently if your buffering power is different.
Absolutely.
So if you added infinite pH buffer into your medium, you'd never see any ECAR, but it wouldn't affect how much lactate the cells are making and how much oxidative phosphorylation they're running, because at the simplistic level, the cells don't care about the buffering power in the medium. They don't know it's changed. It's just how you measure what's going on.
Yeah. Other questions? Do you feel like you are confident and fully able to use the ATP calculation sheet? Or at least you're confident that you'll get there?
I'm actually going to try and use it to say that the glutamine isn't getting oxidized as I add it.
Sounds great.
And we'll see how bad the traces look, but I'll send it to you.
Well, I've done well then. Everyone's going to take this away and bring it to their labs and say, do this and not that.
The sheets are very helpful. There's no doubt about that. And I think once we play with it a little bit, should be able to be confident, like you said.
I mean, the other thing that I hope that you take away isn't just that you have a tool to use, even though obviously we think it's a valuable tool and you should use it, but that it hopefully will be easier and clearer when you're evaluating the flux data of others, what it might mean, what more information you would need to evaluate the interpretation that they make, whether or not the data that they show matches the thing they're asserting happens. So I hope it gives also a better context for what you can do with extracellular flux data and what extracellular flux data can contribute to your hypothesis testing in all of the ways that we've talked about. All right, well, I'm happy to talk more offline and tomorrow, but thank you all for sticking with it. I know these are long days, so thank you.
Thank you.
Thank you. Thank you.
Thanks.
Thank you, Shona.
Thank you.
Good night.
We're done for today then, right?
We are done.
Excellent.
Really? Well, you get brownie points.
Well, we'll see you guys tomorrow then.
See you.
Yeah, bye.
Thank you.